Exercise 1.19. Part A. Show that the collection of vertical intervals in the plane is a basis for topology on R2. We call this topology the vertical interval topology. Well, this collection consists of Cartesian products of these two sets. The elements of our Cartesian product, like this, are ordered pairs of, in this case, real numbers, such that the first real number is in this set, so it has to be A, and the second real number is in this interval, so it has to be between B and C. And so it would look something just like this. You see why it's called a vertical interval. So we want to prove that this collection forms a basis for a topology. And to do that, we need to check the two properties of a basis. For the first one, we can just say that any point xy in R2 is contained in, well, in some set from the collection, and x times, well, we need an interval containing y. How about y minus 1 to y plus 1? That'll do. So that takes care of the first property. And for the second property, we are supposed to assume that we have a couple of sets in the collection which contain this point xy in R2. And so what do we know about these B1 and B2? Well, then B1, well, if it contains xy, it must be x times some interval from, let's say, B to C. And that interval has to contain y, so we have with B less than y less than C. And similarly, B2 is going to equal x times, how about D to E, with D less than y less than E. All right, and I should probably say for some B, C, D, and E in the real numbers. Okay, well, oops, try again. It follows that we have the point xy is contained in, this is going to be my B3, it's going to be x times the open interval from the max of the left endpoints B and D to the minimum of the right endpoints C and E. That's a base element, or it's an element from this collection. And that in turn is a subset of both B1 and B2. So we're done. We found a B3 which contains the point xy, and it's contained in the intersection of B1 and B2. All right, so this collection of sets does form a basis. So we have this vertical interval topology. Now what we want to do is compare it to the standard topology on R2. So in order to do that, let's fix some terminology. Definition 1.2. Let X be a set, and let T1 and T2 be two topologies on X. If T1 is a subset of T2, then T2 is said to be finer than T1, and T1 is said to be coarser than T2. Furthermore, if T2 is finer than T1 but not equal to T1, then T2 is said to be strictly finer than T1. Strictly coarser is defined similarly. So this is illustrated here. The large rectangle is the set X. And then to get the topology T1, let's just draw these two solid lines here. You can ignore the dotted lines for the moment. And the open sets in T1 are going to be the empty set, of course. And each of these four rectangles, and also any union of those rectangles. That gives a topology. And now we want to get a larger topology T2, which has more open sets. To obtain that, I'm going to further subdivide my set X here by these 4 dotted lines. And so now I have these 16 little rectangles. And the open sets in this topology T2 are going to be the empty set again, together with these 16 little rectangles and any union of them. Okay? So we get everything in T1 together with a bunch of new open sets as well. And since T2 has more open sets, you can think of it as sort of being higher resolution. It's going to be called a finer topology, and T1 will be a coarser topology. Okay, and in this case, because the two topologies are not equal, T2 is actually strictly finer and T1 is strictly coarser. All right, one more ingredient before we do part B. Theorem 1.12. On the plane R2, let B be the collection of all Cartesian products of open intervals. These are going to be called open rectangles in the plane. And this collection B is a basis, and the topology T prime generated by B is actually the same as the standard topology on R2. Okay, so remember how we defined the standard topology? It had a basis of all open balls in the plane, centered at any point x in the plane with any positive radius epsilon. Right. Now this new collection, this new basis, consists of all open rectangles that look something like this. And it turns out you can get the same open sets from both bases. Okay, so anything you can get by taking an arbitrary union of open balls, you can get the same set by taking a union of open rectangles. That may seem a little counterintuitive at first, but one of them has these corners, right, and the other one doesn't. But just think about it. It works out. Okay, so part B asks us to compare the vertical interval topology with the standard topology on R2. We want to know whether one of them is finer or coarser than the other. And it turns out that the standard topology is a proper subset, meaning it's a subset and it's not equal to, of the vertical interval topology. So I'm going to abbreviate that by VIT, vertical interval topology, is strictly finer. And said in another way, the standard topology is strictly coarser. Okay. So how do we do this? Well, we need to show that the standard every open set in the standard topology is contained in the vertical interval topology. And according to Theorem 1.12, every open set in the standard topology is a union of open rectangles, okay, of the form A to B times C to D. And each of these, you will notice, is a union over all x in the open interval from A to B of the singleton x times the open interval from C to D. Okay. So I'm basically saying that if you take an open rectangle that's made up of a whole bunch of vertical intervals, just sort of vertical slices at all these different x values between A and B. So therefore, put those two things together, every open set in the standard topology is a union of these vertical intervals, and therefore is also open in the vertical interval topology. Okay, so that shows that the one topology is a subset of the other. Now, to show that it's a proper subset, we need to we need to show that topologies are not equal. Okay, so to show that the topologies are not equal, we must find a set that is open in the vertical interval topology, but not in the standard topology. Well, just about anyone will work, but how about the basis element 0 times interval from -1 to 1. right? That's a basis element for the vertical interval topology. It's a vertical interval. All right, well, if this set were open in the standard topology, then we know that there exists some basis element of the standard topology, which, well, let me not get ahead of myself here. Then there would exist some open rectangle, right? Because we know that those do form a basis for the standard topology. AB times C to D, such that the point 0, 0 in our original vertical rectangle here is contained in A to B times C to D. Okay, I'm going to work on the typing here. And that this in turn is a subset of 0 times -1 to 1. Right? But that's impossible, right? This would imply that, just looking at the first component from these Cartesian products, would imply that the interval from A to B is a subset of this singleton set consisting just of 0, right? Which is impossible. Okay. So we've shown that standard topology is a subset of vertical interval topology, and they're not equal. Therefore, it's actually a proper subset. And that finishes the proof.